output will be another compiler. It will be once again a compiler that takes C as the input language. It will be once again a compiler that produces i386 code. It will once again be a compiler that executes on i386 machine because it was compiled using a compiler that generates i386 machine code. Right? So we have C here, we have C here, we have i386 here, we have i386 here, we have i386 here, we have i386 here, we have GCC here, we have GCC here. Are these compilers same?
Yes.
Yes? No?
One was built by CC and the other was built by GCC.
So?
Potentially generate different code.
Beg your pardon?
And they could potentially contain different code for the same.
So he claims that they need not be same because one was compiled using CC and the other was compiled using GCC. What's your name? Sorry? Senthil. So how many of you agree with Senthil? 1, 2, 3, 4, 5, 6. You don't have too many friends here. Only 6 people supporting you. Okay, those who don't agree with Senthil, can somebody give me a reason why what he's saying is not right?
So the functionality is same. The instructions indicated may not be same.
Functionality is same?
Yeah.
Same? Identical?
Should be.
Should. I want must be or is not. I want a deterministic answer. Anyone who would like to either refute what Senthil said or would like to support what Senthil said? Yeah. Yes. 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 Functionality is identical. Okay, let's take this question. How many of you agree that functionality is identical? Senthil, what do you have to say? Is functionality identical? Let's assume library is the same. Let's keep library around. It's an external thing. How many of you think functionality
Should be identical.
Just calling a arithmetic expression or like a
good question. What do you mean by functionality? No, I would like to refine. I would say functionality will be same if for same C program the target program will be identical. I mean both of them can compile a C program is different, but do we guarantee that both of them will compile C program exactly in an identical manner? No. So functionality won't be same, may not be same.
May not be identical.
Senthil, I am trying to get more supporters for you. Now, would anyone like to change one's position? What do you think? Yeah.
I think the first compiler is just an implementation for C language. Second one is also included for C language. They can have their own interpretation for some undefined schematic of C. They might be different.
Both these have been created from the same source. Both of them have been created from the same VC.
So the stage 2 build will be obviously a bit better than stage 1. Just that the functionality will be similar. Just the produced code, the target code that will be generated will be improved in performance.
The functionality is different.
On what ground? Just because being done again, right?
Stage 1 target language is used as an implementation language in this stage 2 build. So that is why it might be better.
Okay. Yeah.
So I think we can just compare it after that stage build.
We can. What can we do?
We can just do a comparison. We cannot make an entire executable with that like a With the stage 2, we can make an entire exercise. I mean, it is that is just a PC. It is an entire driver.
No, I'm not comparing it with this. I'm not comparing it. I'm comparing these two. Stage 1 build and stage 2 build. Yeah.
Go one level more ahead. Like build another compiler in stage 3. Then how do we compare? So it should be the same.
We'll come to that question later. Okay. Now, yeah.
That's why I think that the compiler that is generated in stage 1 and stage 2, they should be same. Because if we continue like this, all the compilers that are generated, they should be same.
Yeah, Dhananjay.
I think the picture will be clear.
If I do the next.
No, if you assume that the first top CP has some growth term, I'll tell you which term. First is partial evaluation done wrongly. So double ampersand means single ampersand. Double or means single or. Growth term. Third term, when you multiply to 13-point number, it adds an error of 1% for every number. So CP is downright bad compiler.
Okay.
First thing.
Okay.
Okay, then there's no question of good compiler, bad compiler, little better compiler. We are talking of whether something is a right compiler in the first place. Am I talking sense?
Yeah. Okay.
Then the picture will be clear.
Okay.
Assume CC has growth. Which is not just little bad or worse in optimization, it does things wrongly. Then the picture will be clear.
Yeah.
I guess I see in the same code for build 1 and build 2, it will be same.
Okay. So let me close the discussion here. The main difference between the two, and first of all, they're not identical. It's very easy to see they're not identical because they have been compiled by different compilers. I mean, CC, for example, may not be doing dead code elimination, whereas GCC may be doing dead code elimination. Okay, GCC may have a different kind of an optimization. So although on the surface everything looks same, they've been produced by different compilers. Okay, and therefore what we need to do is to go for a third stage build. Once again, we create a build. And now these two compilers, 2 and 3, have been produced by the same compiler. They've been compiled by the same compiler. And therefore, we require that they should be bit by bit identical. This does not prove that the compiler is correct. This is not a sufficient condition for proving correctness, but this is a necessary condition for proving correctness. And there is a reasonable chance that the compiler may be correct, because in this three-stage build, what it essentially means is we have actually compiled 3 million lines. And therefore, this is what is native building.
No, but the last part cannot be assured. If GCC source has certain growth errors,
No,
they
it
will
should
continue to be exactly growth errors in the.
So therefore,
last
it is a necessary condition, but not a sufficient condition. Just because it's bit by bit identical doesn't mean that the compiler is correct. It may be wrong. It may have bugs.
And these two are equally wrong.
Equally wrong. But if they are different, then the chances that they are wrong are very high. Okay, so let's talk about configuration and building. So this is what we specify. We say cd build, and then we configure, and the output is a customized make file, and then we run make. This is what we specify. This is what we externally specify. What happens internally is something different. Okay? What happens internally is that there is a process of generation. Okay? First, generator programs are built. Generator sources are read. Because we want to generate a compiler, we have specifications. So first of all, those generator programs have to be constructed. So first, generator sources are read and generator executables are created. Okay? Then machine description files are read by the generator executables, and lot of source code is then created. And then this source code and the generic source code which is there in source D is compiled together. This is the meaning of my saying in the morning that generic code is copied. It is not physically copied. It's just that this source is in the build directory, that source in the source directory. We compile it from there and put .o together here and link them. Okay? And finally installation happens. And we end up creating generators like this. This is what explains the presence of all those 37 or 27 odd main functions in the GCC source directory, even if we ignore subdirectories. Those are the main functions of the generator programs. We don't have a single program as a generator. There's a program that will generate this part of the compiler, there's a program that will generate that part of the compiler, there's another program that will generate something else. That is the reason why we have so many main programs. And now it's easy for us to figure out which one should be the main function. And we will see tomorrow morning how to identify that main function and how to look at the control flow of GCC. Okay, so how do we examine build process? So we have, these are generators. They will generate the backend. These are handwritten. So they would, for example, parse the machine description file. One would generate, so you would find something called gen automata, gen conditions, gen constants, gen checksum, gen attr tab, gen output. Gen automata is what is going to generate the recognizer. Okay, so different parts of the backend are generated by different programs, and these programs are compiled. Configure script only generates the make file. Okay, it's the make script that will do all this. So, just to summarize, what will the make script do? It will compile the generate. So, see, in GCC directory we have generator sources. We have files with genautomata.c, genoutput.c, genrecord.c, etc., etc. So all these programs will be compiled into respective executables. Who will do that job? It's specified in the make file. Then the make file will invoke these programs. These programs will read the machine descriptions. And after reading the machine descriptions, these programs will then generate C source files. And then these C source files will be compiled with the existing source files. That is the process of building. Yeah?
These are buildings, can we execute them individually?
Yes. Very much.
That's possible. That means that if you want to just generate, let's say, the scanner or the parser, so one of the files possibly might be done.
Scanners and parsers are not generated. These generate the backend part of it. But you can generate various files using this. All that you need to do is you need to know the arguments that are required in order to run these. How the paths are to be set up, where the machine descriptions have to be read, where the file has to be generated. But yes, you can run them. You can see in the build directory they are actually executables. Okay. So how do we examine the build process? So we have something called a build browser. This is an assignment that I gave in CS 715 course. Every year we would ask students to go through the make files and discover dependencies, and these were generated make files running in 6,000 lines, and there was a make file in every subdirectory. It was very confusing. Last year in the workshop, for example, we asked the participants to look at the make file, and that has not been satisfactory. But this year we thought that we can do something more creative. So instead of looking at make file is something that prescribes what is to happen. We thought that instead of doing that, we can do a postmortem. We can do a post facto investigation. We'll run the make, and we can record the output of make, the log of make in some file. Now that file contains all the information, exactly what has happened, which file has been constructed out of it. So I asked my students to do an assignment where they will consult make.log and will write a program which will tell us which file was created out of which file. This is the result is we picked up the fresh program written by a student. So you will be using this in the lab today to examine the dependencies in the build. Okay. Currently it can handle only CC1, reads logs post facto and collects dependency information, and you can give queries to this. You can say, I want to find out which file was created by genrecord. I want to find out which file needed to read MD file and so on. Of course, the queries are not in English. There are dependencies, and there is an assignment which defines all this. So you have to use this in the last session. Let's come to a cross compiler. Let's say we want to build we just looked at native compiler. Let's now talk about a cross compiler. Assume that we want to build a MIPS cross compiler on i386. So our build system and host system is i386. Okay, I'm going to build my compiler on i386. I'm going to run my compiler on i386, and I want to generate code for MIPS. So this is my specification. I have been given a GCC source. I once again take a native C. This time, however, I specify my target as MIPS because I want to generate a compiler that will generate MIPS source code, MIPS executable code, right? So I compile GCC out of it. What am I going to get? I'm going to get a compiler. That compiler is going to produce MIPS code because we have specified the target for MIPS. This is our stage 1 build. Okay. Now if we go for stage 2 build, we can compile GCC source once again with this. What will be the output? Input will be C, output will be MIPS, executable will be MIPS. So we'll end up getting something like this. But this is not what we want. We wanted the compiler to run on i386. We didn't want the compiler to run on MIPS, right? So which means that this is actually this is something that does not make sense. It's inappropriate. As we shall see shortly, it's actually infeasible also. That's the meaning of the statement when the documentation says that the build stops after first stage for cross compiler. This is the meaning. Okay, let's look at a more detailed look at. Let's take a more detailed look at building. So we have a source program which is given to GCC. We saw this picture earlier. So what we do is we basically get these, generate these, but this is something that we reuse. Okay. Existing executables are used directly because in order to get an executable, we need an assembler, we need a linker, we need a library, and so on. Let's call these as binutils, binary utilities. Okay. Let's assume that we are not build binary utilities. Okay. We repeat the same exercise. This compiler will be incapable of generating MIPS executable because we not build binary utilities for MIPS. I need an assembler for MIPS. I need a linker for MIPS. I need my libraries for MIPS. I don't have that. So this compiler is at best CC1. It can only generate MIPS assembly. And because it can generate only MIPS assembly, I really cannot create executable out of it. Even if I give GCC source to it, I cannot create executable. I'm going to get an assembly program corresponding to GCC compiler. So stage 2 build is actually infeasible for cross compiler. We need to do something else, and we will shortly see what we need to do for a cross compiler. Okay, let's magnify the picture still more. Let's look at exactly what happens under the hood. So we have this native CC plus native binutils, binary utilities, and we feed GCC source. Let's look at stage 1 build. So we create libraries. Remember the grammar of our pictures. Ovals are libraries, rectangles are executables, and plain names are files. Okay, there are these kinds of libraries that are required, that are built. Let's not worry about the details. Then we create a library called libiberty, which is a library that is used by a compiler. This is a program called fix includes, which changes the include conventions. Then there are these generator sources. Then we create a CC1 and then we create a CPP. Okay. CC1 and C preprocessor together create an executable called XGCC, which is a GCC in the making, which is a GCC driver in the making. Note this edge here. Gen star is used in creating CC1. These are also used in creating CC1. Okay, because backend of the CC1 was generated using these generators. Okay. Now, when we combine binutils, target binutils, existing binutils, we now have a full compiler that can create executables. this compiler can create executables. So using that, we actually create libgcc. What is libgcc? The emulation library. My hardware may not have all the operations, so I may want to, for example, I may have a fancy multiplication, fmult, fancy multiplication, which is not there on the hardware. So I have an emulation library for it. That has to be compiled. Then my compiler will be complete. Okay, right now I have used libgcc as a part of existing binutils. Okay, these things all together will form CC plus binutils for the next stage, and the whole process will be. So compiler files, stage 1 files are created in stage 1 GCC, stage 2 files are created in subdirectory called previous GCC, and stage 3 files are created in build/GCC. Main driver is XGCC, C compiler is CC1, C++ compiler is CC1+. Then there is something called LTO driver. We want to spend time on it tomorrow, called LTO1, the link time optimization. That's actually a separate process, a separate executable, which re-invokes the compiler. It's a very interesting arrangement that we shall see tomorrow. Okay. Now, so this is what happens in configuration and building. Difficulty in building a cross compiler. In order to build GCC, this requires compiling libgcc. We just saw that libgcc, without libgcc we can't have a full compiler, because the compiler would not be able to generate some operations. Compiling libgcc requires building binutils. Okay. Building binutils. I'm going to compile binutils. I can compile them only using my compiler. So this is circular dependency. This is the reason why building cross compilers using in any kind of cross compiler is not easy. In particular in GCC, we have to somehow break this dependency. Then and only then, we have to break this dependency cycle. Then and only then we can build a cross compiler out of it. So what do we do? I'm going to run through this. This is going to be slightly abstract. It's very hard to explain at a conceptual level, but I'll try to be as precise as possible. There's a sequence of instructions, maybe 15 slides, on the steps that you should take to build a cross compiler, and we have verified these steps. 30 students multiplied by 10 times each, and we know that that works. So we have a GCC source, we have a native C, we want to generate a compiler for MIPS, so we feed this. However, we say, please give me a compiler without libgcc, and don't worry about headers. Don't worry about finding include files. This is the reason why the circular dependency exists. So we break that circular dependency. So don't worry about libgcc. Give me a cross compiler anyway. I know that I won't be able to do everything with it, but still give me. So I build a cross GCC1. Okay. Now I install kernel headers and something called eglibc, a library. I compile that using cross GCC1. That gives me some initial libraries. Okay. Now I have some libraries. I didn't have libraries before. Now I feed these libraries and to the native CC, and now I don't say don't build headers and don't build libgcc. I actually build a cross GCC2. Once I have cross GCC2, now I take full C library source and I generate my final libraries. Now I have built my libraries completely, and now I feed those libraries and I get my cross compiler. In a nutshell, this is the picture. Okay, you can carry out these steps and you can see exactly how it works. And you can compile any C program using this, and you can get MIPS executable. There's some problems that we observed with native build in Ubuntu 11.04. GCC expects a directory called ASM in USR include. In Ubuntu 11.0.4, it's present somewhere else and not here. For some reason, Ubuntu folks have moved the position of the library. Okay. If we install this package called GCC multilib, it creates the required symbolic link, so it works. We saw that this was a fix to these problems we have not seen, maybe there are other problems as well which we have not come across, but this is something that we have discovered. Okay. So what are the common configuration options? So we can specify minus target. This is necessary for cross build. We can specify a string, which is the host, that is the target, the host machine, the CPU, the vendor. We can say enable languages. So this, target, what is the CPU, what is the vendor, we'll see examples. And then we can specify a comma separated list of language names. We can say enable languages. Usually we have been doing experiments with enable languages equal to C. We not looked at C++ or Java or whatever. Then we can say minus prefix equal to install. So this is the directory in which the generated compiler is going to get installed. And we can say minus program prefix in case you want to separate it from the existing GCC. We can create minus disable bootstrap to build stage 1 only. Often it is useful, in particular for doing experiments, to be able to avoid doing a 3-stage build. 3-stage build typically takes anywhere between 45 minutes to 1 hour, depending upon the machine that you are working on. So therefore it's very time consuming. We might fix a small thing in a pass, or we might want to test out something initially. Maybe finally we'll do a 3-stage build. But for experimentation, we don't need to do a 3-stage build every time. We can avoid that. So what we do is we create a new target called CC1. Because for us, CC1 is the compiler. CC1 is what takes a source program and generates an assembly program. So we can add this to makefile.in. Make sure that you add it to makefile.in and not makefile. Because if you add it to makefile, you want to run the configure, and configure is going to override the makefile. So therefore, add these 3 lines to makefile.in. Then you configure, and in order to build, say, make CC1, that's going to take something like 10 or 15 minutes. So you have the core compiler ready. You can also, one of the things that you could do is, you could install this CC1 in the place of the previous CC1. This is a separate executable, and there's a directory where it is there. So then you can use the GCC driver to invoke this. You don't necessarily have to run CC1 compiler. So just a summary, in order to configure and build GCC, choose the source language. For example, minus enable languages equal to C. Choose installation directory, the absolute path. Choose the target for non-native builds. For native builds, you don't have to specify the target. And configure with the choices, and run make in order to generate the target specific part of the compiler. In order to build the entire compiler, run make install to install the compiler, and then redirecting the standard output and redirecting the error output, stderr output, to files is very useful, because it's a time consuming process. If it stops, you would like to know what all it has done, how it has done, etc., etc. So this is a very useful thing. Sometimes your build could fail. If your machine description specification is incomplete, the build process would be unsuccessful. If your machine description is complete but incorrect, then you may be able to build a compiler, but the compiler may not work correctly. So you might get ICE, internal compiler error, or signal says that there is a segmentation violation. Let's look at the last topic for the day, registering new machine description. This is something that you will have to do as a part of the assignment. So we have to define a new system name, typically a triple. For example, we can say spim GNU Linux. We have to edit this directory called config.sub to recognize this triple. We have to specify this triple in the directory config.sub, and we have to change this file config.gcc to define any backend specific variables, any backend specific files, and something that is used as a backend directory for recognizing system names. So because we want to add multiple descriptions, we may work with spim0, we may work with spim1, we may work with spim2. We basically add this in this file. After the case basic machine, we add this. A separate instruction sheet will be given to you. So say recognize spim star spim star dash star, and then you say something that look here there is a particular place for a case, and you say spim star dash star dash star is CPU type equal to spim. This basically says that whenever you specify something that has these 4 characters same, its machine description files are to be found in gcc/config/stem. And then you have to specify the names of the machine description file, the names of the header file, etc. So we create something called a file base, which basically strips off all the dashes from there, and then we specify with the file base, the target macro file is .h file, the target machine description file is .md file, the C file is this .c file, and this target macro prototype file is protos.h. This is what we specify. Okay, and we are interested only CC1 compiler, so we use make CC1, and that's what we do. Okay, so these are the instructions that you have to follow. There are other instructions about building a cross compiler, etc. These are detailed instructions which we are not going to cover. There are few slides on testing also. We will not have a lecture on it, but when you want, there's no point in also reading it. You should, when actually you try to build, then it makes sense to read it. Try to do these commands. So yeah.
Assembler and no English. It's obviously no, they have a no assembler can use that.
We don't, because we want to build only CC1, we are doing this. Otherwise, you have to specify whatever you want to do. This is for spin that we have done. Okay, so just to summarize, what have we seen today? We have seen the basic concepts of configuration and building. We talked about bootstrapping, then we talked about bootstrapping in the context of GCC. We saw what the native build means. We saw the difference between native build and cross build. We saw exactly why a 3-stage build is required for GCC. We saw the commands, and we opened up the hood a little in the morning, which said that GCC is a generator program. It's not a compiler. We saw when we build GCC, actually generator programs are built and a lot of source code is generated. So we have started opening more and more details. However, there still is an external view. Tomorrow we are going to take an internal view. Tomorrow we'll talk about the source code, the data structures, the algorithms, etc. Okay. So let's stop here for the day.